kind of rustles and shuffling around. So just a warning about that. And then the third point is, if you're online especially, we'll have a Q&A session at the end, but we'll be opening the chat after the talk. So if you've got a question, please put your question into the chat at the end of the talk, and we'll come to that during the Q&A session. Okay, I think that is the practical stuff. As I said, I'm really pleased to be able to introduce Angeliki Katsenou to you all. She is a senior lecturer in network media in BDFI and My World. Before that, she was a Marie Curie Fellow and a Leverhulme Early Career Fellow, both here in Bristol. So most of her research revolves around video technologies and streaming. She's done lots of interdisciplinary research about the quality of experience, and has collaborated with industry, including with Netflix, Amazon and YouTube. Her talk today, I think we'll hear some more about this in her talk today, which is called Demystifying Video Services, Quality, Efficiency and Sustainability. And she's going to speak for about 35 minutes, and then we've got a good chunk of time for questions and discussion after that. So I will hand over to you.
Thanks, Becky, for the introduction, and thanks everyone for coming here, friends and colleagues. The basic structure of this talk is around, of course, video services. So because the audience is quite wide, and in terms of the background, what I thought was to give you an introduction on the basic concepts around video services, and then try to respond to some basic questions that my research has also evolved around. So how can we ensure quality when we stream videos? How does streaming actually work, and how can it work in such a large scale? What is the environmental impact? A question that is really important and has become even more important over the past years. And I will give you some future directions that are related to BDFI and my future work. So this is an oversimplified diagram of the basic parts of video services. So we usually have, does it have the pointer right? I don't know if I can point actually on this, I'm not sure. So I will point with my hands, I cannot see the laser. So usually you would have professionals from the creative technologies that are involved in production, capturing the videos, and then in post-production, applying those special effects, doing color correction, color grading, and more stuff. And then that is usually fed into the service providers, like, for example, Netflix, right? Or Amazon or Hulu or anyone. But over the past decade, we have also the users feeling and acting as creators. So usually the most common thing nowadays, of course, is to have a phone and create content and share it over TikTok or Instagram or anything. So all this production part is actually our smartphone. That all is basically distilled into a smartphone that is doing all the color corrections, with actions, of course, coming from the users. Once the user has created their content, they usually upload it on a social media platform, and from then on, what happens, the user can no longer control. So our mystery box is video service providers. And another mystery box is, of course, the networks. That is not like the cloud we see there. It's very complex, it's very heterogeneous, and it makes a really good job in delivering all the experiences to us. The final control point are the display devices and the users. So we have many different display devices. We all are watching and consuming videos nowadays in our phones, tablets, laptops, or smart TVs, and so on. And as you can imagine, all these different devices have different specifications, different requirements, and so on. So these are some facts from Cisco. I don't know if I can move here. Doesn't feel comfortable. So some statistics from Cisco, they reveal that We have about 5 billion internet users. The numbers are huge if you consider that Earth's population is about 10 billion. And then we have more than 20 billion network devices. And those devices are, of course, not all video consuming or video streaming devices, but they could be any other type of devices. However, the majority of those devices are video streaming or video consuming devices. There are different types of networks. You can see on the graph over here that still we have the majority of the world is on 3G or 4G. Then we have countries that operate on 5G and some other types of networks as well. What is also interesting is that the YouTube only uploads are calculated or estimated about 300 hours of video per minute. Can you imagine the volume of that data being uploaded on the video service providers and then all the journey it needs to take in order to reach us? So we come and see in this basic, very simplified diagram that there are some major challenges that the video streaming services need to address. The first one is the volume of the captured video and the data that is enormous. The second one is all the processing that's happening in that blue box in order to make it feasible to stream to the users. The third thing is that heterogeneity of the different network infrastructure and the different devices that adds even more complexities. You cannot, you don't have, let's say, the same bandwidth that you had on a 3G network, if you think about it. So it means you nowadays you can stream more content in your new networks and the new generation of networks. We have the user experience and behavior that is actually quite difficult to capture. Well, the first reason is that human eyes do not operate the same way as all eyes do. So what is good for me, for example, is not good for Karen or for someone else. But also the behavior is sometimes difficult to predict. For example, people like me, when I'm cooking, I'm also streaming stuff. So I'm not paying attention, I'm just listening to it, right? So the quality wouldn't matter in that case. But that is a behavior that's not easily captured. But at the same time, it does have impact on the streaming services and potentially on the environment as well. The biggest and most important thing, of course, is the scale that makes any type of solution for video streaming very difficult and challenging to implement. The first thing that is important to talk about, and that's actually the basic enabler for video streaming, is video compression. You're all probably familiar with the concept of compression that comes from compressing any other types of data, right? You compress the files to send over to a friend when the size is over 20 megabytes, and you can not just drop them into an email, for example. Of course, nowadays we have cloud sharing that makes things easier, but that is what we used to do with documents. So what we need to do with video coding, of course, is we need to compress, because if you think about it, for 1 second of video at 4K 60 FPS, we need about 1.4 gigabytes if it's raw, when it's raw, not when it's encoded. You're all aware probably and familiar with the containers like MP4 or .mov. Those are encoded, those are compressed files. So if you have a raw file, something that's coming from a red camera in a studio, for 1 second, you would need that much. And you can imagine that for 1 hour of a video, you would reach about 5 terabytes. So just think of your favorite series that spans over 3 or 4 seasons. And then if you make the calculation, you can easily understand the enormous size, or if you think the catalog that Netflix has or any other company. So what happens usually, what is compression? In simple terms, you try to reduce and remove information that you can easily regenerate and restore on the other side. For example, when you're capturing a still frame, an image, you use the color and spatial redundancies that exist within the same frame across different blocks. So you split your images into blocks, and then you try and find the resemblances in colors or information generally that you can easily repeat. The same happens for video, but because the video captures a sequence of still images, you're trying to find the motion associations across the different successive frames. So you're trying, instead of just doing a spatial encode, you're also trying to do the same thing for motion, to predict the motion. In this example, if you look, the majority of the pixels are exactly the same from frame to frame. What changes is that person actually moving. So it makes sense to be able to encode that motion and be able to predict that motion and reduce the spatial information, for example, in the first frame only, and some other significant changes across frames. So that's the basic idea of compression, and that is something that people have been working on. But let's see some effects on this video. Do you notice any differences between those videos? Any volunteers? Karen said, wait, no.
Well, I looked at
using
it and I was like, I can't really see any difference.
So this is a successful example of compression. Successful meaning that we managed to reduce a lot the file size so that we can fit it into a channel at 5.2 megabps without compromising the quality. For those who are online, probably Teams or any other tool we're using is making some extra compression. So I don't know, perhaps you're able to see small differences or not. But the idea is that successful compressions should actually result into something of similar quality, but at a much smaller file size that you can easily fit over different networks of lower bandwidth. But what happens when I try to compress it and push it even harder? Then I get something like this, which I think we can all agree that we see the differences. We see some annoying artifacts. And the idea is we further even compress this down to 1.2 megabps. And although we can stream this easier over slower networks, we can all agree that whoever is viewing that would not be as happy. Of course, a major parameter related to the quality of the experience has also to do with the device and the environment and the context we're watching. If this was here, if we had like our favorite actor, Brad Pitt, for example, I would compromise seeing him a bit blurry. But if it's some other type of important information that I wouldn't like to miss, that should be fine. Or if I paid a lot for this service, I would be then annoyed that I'm getting this one, right? So that result that you saw is actually the effort of decades of people working, of technologies and scientists working around video compression and video standards. This is a timeline of the proprietary in the bottom, the green ones are the proprietary video compression standards that actually when someone is using that at a consumer scale, they need to pay for that. But since 2008, Google started developing a royalty-free codec that at some point convened with other companies, and they have created the AOM, the Alliance for Open Media. And in the Bay Area, a lot of big companies like Apple and so on, they have released AB1 codec that is currently probably what you're using on your phone if you watch something on Google Chrome. It has also been implemented now in some hardware devices. I think LG was selling that had the hardware version of the codec. All right, so how is the quality of experience ensured? How can we measure quality? How can we understand what viewers are watching? Of course, as we saw earlier, depending on the compression level, you have different levels of quality. So if you look at this diagram, this is a comparison across two different coding standards. When you try to squeeze down, you basically reduce the quality. So this is less bits. If you go to the left of the horizontal axis, it's using less bits, compressing more. And then because it's dropping down, it means lower quality. But as you can also see, there is a different curvature on these two curves. And also the latest HEVC standard that most of the new smart devices are using now, it has a better performance than the previous one. Between the different families, there is about 50% of improvement in efficiency, in coding efficiency, which means 50% better quality for about the same bitrate. All right, as you can see, same bitrate. This is same bitrate. You get about how much is it? 4 dBs, about 4 dBs of improvement. There are metrics that actually measure the pixel difference. So PSNR is one of those metrics. Pixel differences or similarities between the original and the compressed one. And then also are some metrics that scientists, and this is actually a part of interdisciplinary research between engineers and psychologists, they have tried and have been trying to create perceptually aligned metrics that take into account human factors, like, for example, motion masking or texture masking, cases where we can actually reduce the number of bits without losing a lot of detail. For example, it's much more difficult to see the errors around in the cactus, but it's more easy to see the errors around, for example, the pot area that is more homogeneous. So a really important part of the reason I included this is because the quality rate curves show basically that trade-off between quality and bitrate, quality and compression rate, right? And that is what we are trying to use generally in the streaming pipelines. Now, the golden standard in evaluating subjective quality and evaluating quality of videos, of course, is performing subjective quality assessment. That is, however, a very time-consuming and difficult process because, as you can actually see, you need to get people in a lab environment, and you need to show them in the controlled environment where you control actually the lights, you control the content you are showing to them, and you ask them regularly to vote for the quality of the content they're watching. And you have to have enough subjects so that your statistics are right and so that you can get statistical significance in the scores you have in order to be able to do that. So a lot of my research has been evolved around performing those objective studies that serve actually as a ground truth and as a basis, a reference, in order to design better metrics. This is one example of a research we did comparing the latest codecs across different types of content. As you can see, it's not easy to tell which one is better across the different. These are rate quality curves. They show the trade-off between quality and compression points. And as you can see, it's not easy to say which one is better than the other. So it's not an easy job to do. But those studies, actually, they help us create new metrics that use deep nets, for example, or machine learning. And then we can improve the existing metrics by aligning them better with quality. This, for example, is a metric we improved. Netflix has released in 2017 VMAF. It's the best metric so far performing at a large scale that is better aligned with perception. And we managed to improve its performance by adding some new features and then by training a dual type of setup of model, combining those models and getting a quality index. Now, how does streaming work? Another aspect of compression that complicates more things is, of course, for the same bitrate, we can all agree that those two videos do not have the same quality. So we have the same number of bits, but the quality is not the same. So the quality and those rate quality curves, they are quite variable. These are rate quality curves across different resolutions for 100 sequences that you can see on the left that are quite different in terms of the content and the motions they have. So in our collaboration with Netflix, what we tried to do was to design a solution that takes into account this heterogeneity and variability of the compression, of the compression performance over different types of content in order to make their system a bit more efficient. So what did Netflix do in the past? They were having, for example, this video down here, and they were compressing for a different number of resolutions. For example, these 4 that you can see here, Full HD, 4K Full HD, HD, and SD, for example. And then they compressed that at different compression levels, and they were trying to find the best combination of those parameters for the different bit rates. So they knew if, for example, Becky has in her home 100 megabps kind of connection, they will send the 4K, which will give her the best quality possible. But if I'm in my place in Greece have only 20 megabps kind of internet connection, then I would get the full HD at the best possible quality there. Right, so before I go to what we did exactly with Netflix, I'm gonna present what is the basic idea of what Netflix started employing since 2015 and YouTube a bit earlier, but in scale since 2016. And that is called adaptive bitrate streaming. We can all agree, and especially people like Rashid and Hule and Xenophon can tell us that the networks are not, they are generally very reliable, but they cannot be reliable in terms of the speed they can provide, the bandwidth they can provide. That is kind of a dynamic situation that depends also on the number of users you have, depending on the type of network, of course. So we end up having an available bandwidth that can be from high to medium and to low. That means that I need to keep track what is happening during the delivery in my end user and actually adapt my what I send to them, adapt the compression level based on the available bandwidth at that moment. At the same time, adapt based on the display device. So if it is a full HD device, or if it's a 4K device, or if it is an SD device, I need to take that also into consideration. And then I need to create an algorithm that takes that into account and delivers the best pieces. So what they started doing in YouTube and Netflix is they have created this transcoder thing that takes actually the video as an input, and then it creates a different number of representations across different resolutions that can meet the demands for different devices, but also across different compression levels that can meet the requirements of the bandwidth here. And then they feed that into the media origin servers, then here through usually a CDN, they get the information of what the bandwidth and bandwidth variability is over chunks of time, and then they send a combination of those representations to the users. So if you think you're watching 4K all the time, you are watching 4K all the time, but it's 4K perhaps upscaled at your display, and it's not originally 4K. You might have been receiving a full HD that is then locally upscaled in your TV. Does that matter? It doesn't matter if what I'm seeing has a constant quality, good quality, right? But it starts to matter when I'm not seeing good things, when I start seeing artifacts. So, as I said, what Netflix used to do is to encode at every compression level, different resolutions, and then that ended up like days of encoding for just one video. What we decided to do is we used machine learning, and then instead of actually doing all the encodes, we started predicting what would be for specific bandwidths, what would be the best combination of parameters or the best compression level, so we end up only encoding at the compression levels we're actually going to use. So we ended up with a methodology that resulted in an 87% reduction of the numbers of required encodes, and that reduced the encoding time from days to hours. And that makes actually a huge difference. And that is something a lot of companies are doing. Some other companies like YouTube, they are actually implementing a different model that is based on popularity. And that is actually the case for many of the social media companies. So, for example, I upload something on YouTube. It's not popular, of course, because I'm not well known. So they just leave it as it is. So they do like a default kind of transcoding. But if, for example, I don't know, Taylor Swift uploads something, then that, of course, because they know she's popular and she's going to get like millions of clicks, they do all this process, the ABR that I was, the optimized version that I was mentioning earlier, so that then they can deliver the best possible quality to everyone. So different business models, and that highly depends, of course, on the use case and the application. All right. So now let's go into something also interesting that is related to the environmental impact of those, because we have talked about a huge number of computation that is either happening on a data center or it's happening locally at a local data center or on the cloud that we are saying. We have talked about different types of networks, and that involves, of course, different types of hardware. We have talked about different types of devices, and those devices, all they have different life cycles. For example, some people change their smartphones every 2 years. Others change their TVs over 10 years, however. So if we want to talk about CO2 emissions, we need to consider, of course, the life cycle of the devices and the technologies as well. That is, of course, something very difficult to measure. Here is a figure courtesy of Dr. Sheen, who has been working on this topic. So it has been estimated globally that the ICT and entertainment and media kind of share of emissions due to electricity use is about 10%. Some people, when they saw this figure in a conference that we're having a similar discussion, some were saying, okay, it's not that much. You can all agree that the manufacturers are to blame, but still 10% globally, it's a huge number. And we all need to do our bits and pieces in order to minimize that. So the idea here is to try and understand where those emissions come from. And as you can see, it's separated, data centers are separated from the networks, for example, and things are separated for the entertainment and media networks. But it is something that tells a big story. You can also see user devices have a huge impact. In the latest report that I'm aware of from the Carbon Trust that did a huge study with funders like BBC and Sky and Netflix, and they tried to basically measure what is the CO2 impact across the streaming pipeline. So they mostly worked on the data centers, as you can see there. They worked on the content delivery networks, what happens over the internet transmission, and then what happens when we reach our homes and we have our home routers, and then our devices. So from that study, it has been inferred that the estimated emissions as a European average, the highest percentage is actually on the viewing devices. And if you think about it, it makes sense because although the complexity of the communications and the heavy processing that is happening from the video streaming services is happening on the data centers and data farms, however, that happens usually only once. Then if you deliver that into millions, then you have 1 million of devices actually running, working on electricity, functioning on electricity that is usually provided by what I called like the dirty sources of energy, so non-renewable sources of energy. And that is the reason why you have a highest CO2 impact coming from the devices. Of course, the good news generally is that although these numbers look huge now, over the years we see a decline because the industries are launching, for example, new devices that are consuming lower power generally. The data centers, for example, are using GPUs of lower energy and so on. So we will see those figures getting a bit perhaps declining in the near future. So in this context, I try to understand how the energy consumption of the latest codecs scales compared to the previous generations. So that here is an example of 4 different codecs. So VP9 is the predecessor of SVT-AV1, and X265 is the predecessor of VDENC, which is a state-of-the-art codec. So we can all agree that when we look at the decoding energy, and decoding energy is actually the energy that our display or our phone, smartphone consumes when they are running something over there. We can all agree that the newest codecs, the yellow and the blue line, they actually are consuming much more energy compared to the oldest codecs, compared to the compression level, of course. That is the cost of having better performing codecs that consume more energy. But a lot of work is actually happening at the time from the standards. They are trying to reduce that impact. Another question is what happens when streaming at large audiences? I think I already mentioned the response was that, of course, everything scales up with the number of audiences. So if I do peer-to-peer streaming, will not have the same environmental impact, for example, as if YouTube is streaming Taylor Swift video, where millions of people are going to watch that. There was also this very interesting research we did with Dan Sheen, where we tried to incorporate the whole pipeline. And this was inspired basically from a regulation that was announced during COVID time, where the EU asked Netflix to reduce their streaming resolution from 4K to Full HD in order to reduce the carbon 2 emissions. So what we found is that there is marginal difference when you reduce the resolution, because again, even if I'm streaming a low resolution video and I want to watch it on my 4K smart TV, locally it will upscale to 4K. So the majority of the energy consumed will be from functioning that 4K 65-inch display. So the electricity I'm consuming remains about the same. Right, so reaching towards the end of this talk, I just wanted to summarize some key directions and enabling technologies that are shaping my research future. I will continue working towards human interaction kind of things. I would like to put human in the center of my research. And this is why I'm headed towards more interdisciplinary research. I would like to measure and understand about immersive experiences and what happens actually in the future. We have that project with the government around metaverse, and that will be a new direction around it. I want to support users as creators, so like making AI tools that can, for example, do some post-processing and remove banding, like help users basically create better videos. I will work, and I'm actually working at the time about on the real-time communication of immersive media. Can we improve and can we drive networks based on the content and on the needs of the content we need to deliver? And I think that's very much aligned with the task-oriented future network kind of key enablers. And then, of course, I intend to continue working on sustainability aspects. I'm currently working on understanding how we can make interventions based on user behavior and basically optimize the delivery of the media based on the energy consumed. And a last pillar around this is basically to have an ethical and responsible design of technologies, take into account what technologies we design, who those are intended to be used from, make them more inclusive, and also as engineers, I think we have the responsibility of thinking of all the ethical aspects of a project. Of course, the key enablers are everything that has to do with future networks, because they are the key enablers of all these technologies. A lot of AI, of course, will be involved. Hope nobody's heard from that. Some hardware aspects as well. And of course, interdisciplinarity. I think that was one of the key aspects of my research so far. I would like to thank these authors, co-authors that have been actually part of the works that I have listed here, some of them from some upcoming ones. And those are some of my basic funders for these works. Thank you all.
Thanks so much. I'm just opening my laptop up. If you are online, the chat function should now be open. So please feel free to put your questions there and we will come to them in a minute. But I wondered whether we should start with questions in the room. Does anyone have any questions? Yeah.
Hello. Congratulations. That was a very enlightening presentation. So I have questions about two of your slides. Slide 27, I think, was the one that you showed what happens with modern compression.
Mm-hmm.
Okay, so the general concept here, or conclusion, is that you manage to encode, you actually manage to compress things more, but then you have to pay a price in terms of energy. But this is only about the compression itself. But maybe you're saving, and I do not know how much, energy from having to transmit that through the network, because that also costs in terms of energy.
Yeah, no, that's absolutely true. That's one
So
of
maybe it's not that bad. That's what I'm saying.
Yeah, could be. However, that's part of one of the projects I'm working now. That's actually seed funded from BDFI. So the change, let's say, in the network is that the energy consumed in the network, first research says it's almost minimal. So what is consuming more energy is on the decoding side.
Okay, so this is a very good take-home message for us, the network people.
Yeah, and these lines are actually averages over a big set of sequences.
So the other question, almost related to that, is about another slide that you showed, the CDN. It was roughly before slide 20, I think.
With ABR, they probably need.
Yeah, I think it's after. Yeah, this is the one. So you do the encoding and the transcoding, the one that actually costs more in terms of energy, before you pass it to the CDN, which is close to the edge of the network. I don't know if you can improve things more in terms of energy or traffic, but I think it's something that we should be jointly doing, us, the networking people, and you people working in the media. Things like when something is being consumed, since the last mile is usually the bottleneck, instead of having to go even back to the CDN, if somebody on the same block of flats watched a very popular movie, go and fetch it from their own cache, for instance, or the popular parts within the video.
That would be on the edge, on the rack.
It could be on the edge. It could be on the extreme edge, which is even your own device, especially if it did the upscaling there. Because if you use the internal network, even within Wi-Fi range between the two devices, you could save up a lot of energy the way that I see it. If it is true that upscaling is actually stealing back whatever benefits you got from deliberately encoding things to full high definition. The other thing is that a short comment. Social networks, they cheat. They create actually popularity trends by nudging, as they call it. So of course, Taylor Swift was another example. But if they don't have it ready yet, they make sure it's not popular enough yet. It's actually them to blame. I don't think whatever you do, you try to improve this. If they keep having this policy, which they will for their own reasons, marketing-wise or even running the network, it's up to them. They're the ones to blame.
Yeah, no, I agree with you. There are a lot of these trends, of course, are reinforced sometimes from the recommender systems and so on. So they kind of pre-know because they bias us, or our preferences that, based on what we have watched already, are also biasing the recommendations we're getting, right? So Xenophon is right about that. So they have some knowledge, so they can kind of drive these more efficiently. That, of course, that depends highly on the business models they have. But thank you. They are all very interesting. I think we should chat more about that pushing to the edge for a paper.
Thank you so much. That was a beautiful and very easy to grasp presentation. I really like it. Thank you.
We have a couple of questions from online. So if we move to those. So the first one is from Sanya, who says, fantastic talk. And has a question around the role of network media in education, both higher education and literacy more generally, and is wondering how do we kind of use network media in education given the preferential treatment from network providers? How can we bridge the digital divide in this space, so to deliver content to vulnerable populations and populations with limited needs?
That's a really interesting question. It reminds me of a project that was running in India. So this summer I attended this Royal Academy of Engineering in Bangalore. It was a frontier symposium, so it was very much addressed to low-income countries and vulnerable communities, and how you can use basically engineering and any type of engineering and technologies to support them. So it is a big question with multiple aspects. I'm not sure I can answer to all of them, but especially for the vulnerable communities, there were two very interesting projects that grasped my attention. One was, there was this British startup that is working with Africa and farmers in Asia as well, that they're using videos and video streaming of animated content in order to teach them and educate farmers on new technologies, basically. I found that very interesting and very intuitive because it can be globalized easily. If you use animation, you don't basically sometimes need to use a language for that, unless you want to specialize a lot, of course. But also another very interesting project that is running in India was about some communities where women are marginalized. So what they did is they created this local private network across villages that women can actually communicate with themselves, and they have educated the women to be basically the ones who operate and run it. And this is an ongoing project, of course. I cannot talk about the impact of this, but what it sounded like, it was something that it could be an enabler towards education, also towards bridging the gap of digital illiteracy, I think. I think that visual communication is much more intuitive, especially for illiterate people. So I think it could be a really good technology to create really good projects and strengthen those communities. Thanks.
Yes.
Thank you.
Okay. So we have another question online from Rishiraj, which is a more technical question, so I will try and get this right. So they're asking whether there are any additions to measure quality when we do not have the source video. So for example, pixel compression and VMAF, these processes require the original video. The use case for this is, for example, a third-party application or a service provider that wants to measure the quality of the content in their network. But also just say thank you for the great presentation.
Thank you. That's a really good question. It's actually a very active research area. I have a PhD student who is working on that. So the first response would be, there is a lot of research around no reference metrics, quality metrics, where you don't actually need the original. So far, those metrics have not been performing that well, but there is a lot of progress over the past years by using deep networks, basically, where a lot of promising metrics are coming out that can guarantee, at least give you some estimation of what the user is actually receiving. I know that the companies like Netflix and YouTube, they also use A/B testing methods, where they actually, I don't know if you have an idea of what A/B testing is. You basically, it's like a subjective evaluation, but it is in a product. You probably have all received sometimes, how was the quality of this call, for example, in WhatsApp or something. So they test technologies and then they ask you to rate. So you don't know that you're actually rating for something, but they do a lot of this A/B testing in order to try to get live responses of slightly changed technologies. So that is my response. Happy to talk further about this topic.
Thank you. I have another question in the room.
Hi, Angeliki, thank you very much for a great talk. I wanted to zoom out a bit, if I may. So I'm an AI researcher working in aerospace industry. And I understand from your talk, when we talk about these sorts of use cases, one of the main goal functions would be quality of service, right? In entertainment-based use cases. However, in highly regulated domains, you have different goal functions, such as robustness, out-of distribution, generalizability, and so on of these systems. And obviously, in many use cases in this domain, you have energy frugal settings, like, for example, in spacecraft that needs to send a bunch of images of a new celestial body, or even something that my team works on, like visual-based landing. So you have computer vision-based navigation autonomous landing system, and you need to compress it in some way, but also to retain important parts of the image. So I was wondering if you're aware how close or far we are from semantics-driven compression, so semantics-aware compression. For example, there is a famous example of an elephant on the runway, right? It's gray, it's sort of crumbly, and it has some sort of weird texture. So does the runway. So you don't really, and it's still on the runway. It's just chilling, And so you don't really want to obscure that part of the image through spatial and temporal invariances, but you want to have some sort of object detection and recognition to say, okay, don't obscure this image. This is really important. Retain the frame rate, number of pixels, and so on. Where are we with regard to this?
That's a really interesting question. I could only answer that it's still research. There are many challenges in this pipeline, and many are related actually to the vast use of AI. Because everyone who is actually related or has worked a bit with AI, they all know that the models you create usually depend on what you train them on. If you train them on images that only contain like cement or the material when you land, they will never get that there is an elephant, right? So I think what is important is generally to improve training, to improve models that are more generalizable. I'm aware that there is a lot of work around semantics recognition and semantics compression, but I'm not sure we are there, like in order to be able actually to use it as a consumer product in the use case, in the example you gave actually. I don't know, for example, even like the Tesla's cars that have really good software in recognizing traffic lights and the lanes and objects, if they would recognize an elephant on the road. So yeah, I'm not sure about it. I think we're not there yet, but it's definitely a very active research area. And usually in CVPR, you always see papers around this research area. Thanks. We can make a project around it, Vedran. Yeah.
Hi, yeah, very good talk. Thank you. It might be leading on from that a little bit, and I'm not necessarily expecting an answer, but as an observation, there's reference about the content production growing all the time, more and more content coming out there, but there's nothing going back into that content from what you've shown. But there's potentially a lot of knowledge and insight that we're gathering from current content that could inform either the content that is more likely to be produced, and then more intelligence about, oh yeah, there's lots of elephants on runways here, and we can learn that this might be something we're going to see more of. But also informing content that's actually worth producing. So there's already a sort of natural selection process going on here with the choice of what to encode with the best technology and so on, but actually sort of informing the content in some way. Is there anything going on in that space?
Yeah, so to be honest, I think there are some pipelines that do actually take into account the content information. For example, what I was showing here in this methodology, I actually was training Gaussian processes that learn those rate quality curves, the content I'm inputting. So it actually learns the parameter space and can really do a good job in predicting for sequences that are not in that parameter space. However, and I'm aware that people are working with content that is quite challenging, like low light image content, and that's looping in information. For example, what is the best ISO setting for specific types of dark low light content, and that could make the post-processing easier and get a better result. Is that what you had in mind in informing back? Because I guess there is some unofficial type of closed loop thing going for creators. Like creators, they know what works and what doesn't. Whether it is an expert system as an AI tool, I think like Nuke and some of these special effects tools that people are using, they already have a lot of deep nets that have been trained on similar contents. So I'm just going to say something here. I'm not sure everybody agrees, but for example, if you wanted to design a network that works really well with low light content, then you would train it on low light images. So that would be a bespoke tool for that. That means that that network probably would be overfit to work for that tool. And in that case, overfitting or overtraining is not a bad thing. So in that sense, I think there are tools that are doing that already. I know consumer tools that are overfit are used by the industry at the moment. If there is something specific you would like to chat, then I'd be happy. And I didn't get your name.
John
from?
So I run a consultancy helping organizations to make smarter use of digital in a broad way. So yeah, so there's a big thing about sustainability now, and some other areas. But, yeah. All right. Thank you.
Can I have a question? Sorry. So the quality of service depends on manufacturers, and ideally we are trying to have a accurate prediction or estimation of these factors in order to have a more accurate, measurement or action for the quality of service. But what would we cannot have a accurate prediction for these factors? Would that affect or degrade this quality of service very much or not? Or in another way, whether we can still maintain the expected quality of service without accurate prediction of these factors?
Thanks, Yulei. I guess when you're talking about quality of service, you're talking as a networks person. So
The quality of service of the video.
the quality of the video.
KPIs, video KPIs.
Yeah. Yeah, because I was thinking about the KPIs of the networks when you talk about quality of service, you usually talk about, for example, aggregate maximum bit rate or something like that, or jitter and so on. But in video, when we talk about quality, we talk about the actual image quality. So the question was, if you cannot control your networks, how that would impact on the image?
For example, if we cannot predict accurately of the network quality and also the user experience and other factors, can we still receive the expected?
Yeah, so you would receive something that either would be rebuffering, or that would have a lot of artifacts that during decoding you would see as strong pixels. So you would get like degraded quality. But the truth is, because networks are usually over-providing, so you have like the maximum usually limits that you never reach. Like even during COVID, where the demand went crazy, like 380% more than before in March of 2020, everything worked perfectly. So you were still receiving good quality videos. And I think the networks have been very smart with that, over-providing so that you can cover the demand and get a good quality.
Okay.
I think the only issue would be if you were streaming at an already very slow network, then you would get something really bad. But if you were streaming in a very good network, then you wouldn't have this issue.
Okay, so that is due to the reservation of some resources already.
Yes, yes. I think the networks have done a really good job, and that it was proven during the pandemic, actually. Yeah.
I suppose with the CDNs, or the content delivery networks, you can obviously spread the load over the infrastructure, over the various different regions, so you're not relying on just, say, the Netflix servers actually sending the data. It's sort of cached all over the place.
Exactly. So the game around networks is quite complex. Those CDNs, those are a different type of network, but they specialize on how basically to distribute geographically also the content. So there is a lot of information going, what is popular in the UK. So those are usually stored locally in the CDNs, and you don't have an on-demand streaming from the origin server real time. So there is a lot of very interesting information around the way those CDNs work and how they optimize.
The business model, if they're working,
Yes, exactly.
if they're working for the content provider or for the delivery network.
Exactly, and what the company is paying, for example, if they're paying for.
That's why Google and Facebook, for instance, they own their own CDN, so they control everything.
Exactly.
Thank you. I'm just aware of the time. I don't mean to stop this discussion. If you're here in person, there will be some tea and coffee outside. But thanks very much for a super interesting talk. I've learned a lot, and you've generated a lot of discussion. I just wanted to end by saying that there are further ways that you can interact with BDFI. We have a range of networking events, seminars and lectures. If you're a member of the University of Bristol, we have an affiliates program which you can join, but we also have a BDFI newsletter there that you can sign up to. We have facilities here, including the Neutral Lab, which is upstairs, the reality emulator, and different collaboration pathways. So please get in touch if you're interested in what we do and would like to know more about it or be part of it. But yeah, thank you very much for attending, and thank you to Angeliki.
Thanks, thank you so much.